In 32 years of studying how nations build military power, I have learned that the most dangerous dependency is not the one that your adversary creates. It is the one that you create for yourself slowly, willingly, over decades of rational economic decisions that each made individual sense and whose cumulative effect nobody in Washington or Brussels or Tokyo was willing to state plainly until the morning it became impossible to ignore. This is that morning. At 6:23 this morning, the Chinese Ministry of Commerce issued a two-paragraph statement. Not a threat, not an ultimatum, not a declaration, a statement. Effective immediately, the People's Republic of China is suspending all export licenses for 17 rare earth elements and their processed derivatives to the United States, the European Union, Japan, South Korea, Australia, and the United Kingdom. 17 elements whose names most people cannot pronounce, whose existence most people are unaware of, and without which the following things cannot be manufactured. The F-35 Joint Strike Fighter, every precision-guided missile in the American arsenal, every semiconductor above a certain performance threshold, every electric vehicle battery, every wind turbine generator, every MRI machine, every smartphone, every laptop, every piece of advanced military electronics that American forces have deployed in every operation this series has documented. China produces 85% of the world's rare earth elements. More importantly, China processes 90% of the world's rare earth elements into the refined forms that manufacturing requires. Even the rare earth elements that are mined outside China in Australia, the United States, and Canada are sent to China for processing because the processing infrastructure does not exist outside China in sufficient scale to substitute for Chinese capacity. America has not just allowed itself to become dependent on China for the raw materials of its military and technological power. It has allowed China to become the world's only processor of those materials, making the dependency absolute rather than merely significant. This morning, China activated that dependency as a weapon. Tonight, I want to walk you through exactly what 17 rare earth elements do, exactly what their absence produces across every dimension of American military and economic capability, and exactly what the timeline looks like for building the alternative supply chain that 30 years of rational economic decisions failed to build. Tonight, I want to answer 4 questions that no mainstream economic or defense commentary is addressing with the honesty this morning's announcement demands. First, what are the 17 rare earth elements and what specific manufacturing processes do they enable? Walk me through each critical application: the F-35's permanent magnets, the missile guidance systems, the semiconductor fabrication, the battery chemistry, and explain precisely why these specific elements cannot be substituted with alternatives on any timeline that the strategic situation provides. Second, what happens to American military production when the rare earth supply stops? Walk me through the specific production lines: F-35 assembly, precision munition manufacturing, naval electronics, and explain the timeline from supply suspension to production halt to operational capability degradation that the American military faces. Third, how long does it take to build an alternative rare earth supply chain? Walk me through the specific steps: mining development, processing infrastructure construction, manufacturing adaptation, and give me the honest timeline whose length explains why 30 years of warnings about rare earth dependency produced 30 years of insufficient response. And fourth, what is China's strategic calculation in weaponizing rare earth supply? What specific moment in the conflict trajectory produced the decision to activate a dependency that China has been accumulating for 30 years? And what does the timing tell us about the relationship between rare earth suspension and every other dimension of the conflict this series has documented? Stay with me, because the answers describe a weapon that was hidden in supply chain spreadsheets for 3 decades and has just been deployed against every dimension of American power simultaneously. If you came here for the analysis that explains why 17 elements you have never heard of are more strategically important than every weapon system this series has documented, subscribe now. Hit like. Share this with anyone whose understanding of American military power has not accounted for what it is made of. Leave your assessment in the comments. I read every one. Now let us get into this completely. Let me start with the elements themselves, because the phrase rare earth elements has been used in strategic commentary for years as a general warning whose specific operational content is rarely explained. I want to explain it precisely because the specific applications of each critical element establish why the supply suspension produces the consequences it produces and why substitution on any relevant timeline is not available. The rare earth elements are a group of 17 metallic elements whose chemical properties, their specific electron configurations, produce magnetic, luminescent, and catalytic characteristics that no other elements replicate. They are not rare in the sense of being scarce in the Earth's crust. They are rare in the sense that they occur in concentration sufficient for economic extraction in very few locations, and that separating them from the ore in which they occur requires chemical processing of extraordinary complexity. Let me walk through the critical military and technological applications. Neodymium and dysprosium permanent magnets. The F-35 Joint Strike Fighter contains approximately 920 pounds of permanent magnets in its airframe, not decorative magnets. The permanent magnets that power the F-35's generators, its actuators, its radar systems, and its flight control electronics. Permanent magnets of the performance required for aerospace applications require neodymium as their primary constituent and dysprosium as the additive that maintains magnetic performance at the elevated temperatures that aerospace environments produce. There is no substitute for neodymium iron boron magnets in aerospace applications. Alternative magnet compositions, ferrite magnets, alnico magnets, do not achieve the energy density that neodymium magnets provide at the weight constraints that aerospace applications require. An F-35 without neodymium dysprosium magnets is an F-35 whose flight control systems do not function. Lockheed Martin's F-35 production line requires a continuous supply of processed neodymium and dysprosium, whose current inventory, based on published supply chain assessments, supports approximately 90 days of production at current rates, 90 days after which F-35 production stops. Not slows, stops. Terbium and europium precision guidance. The laser guidance systems, the infrared seekers, and the inertial measurement units that make precision-guided munitions precise require terbium and europium in their optical components. Terbium's specific fluorescent properties are required for the laser rangefinder components that precision-guided bombs use to measure target distance. Europium's luminescent properties are required for the display systems and the cockpit interfaces through which pilots designate targets. The precision that makes American air power the most accurate in the world, the capability that has defined American military advantage since the Gulf War, depends on a continuous supply of terbium and europium, whose interruption degrades guidance system production within weeks of supply suspension. Precision-guided munitions whose guidance components cannot be manufactured become unguided munitions. Unguided munitions are the weapons of the previous century. Lanthanum and cerium optical systems. The advanced optical systems in American reconnaissance satellites, in the targeting pods of American strike aircraft, and in the surveillance systems of American unmanned vehicles require lanthanum and cerium in their glass compositions. Lanthanum glass, whose specific refractive index and optical clarity properties are produced by lanthanum's chemistry, is the material from which the lens elements of high-performance optical systems are manufactured. Without lanthanum glass production, the replacement of degraded optical components in existing systems cannot occur. The reconnaissance capability that every operation this series has documented, the satellite imagery, the targeting photography, the surveillance data, degrades as optical components wear out and cannot be replaced. Yttrium electronics and armor. Yttrium's applications span both military electronics and armor systems. In electronics, yttrium stabilizes the zirconia used in the thermal barrier coatings that protect jet engine turbine blades, coatings whose absence would reduce turbine operating temperatures and therefore reduce engine performance below design specifications. In armor, yttrium-stabilized zirconia is a component of advanced ceramic armor whose ballistic performance exceeds steel at lower weight. The jet engines that power American military aircraft and the armor that protects American military vehicles both depend on yttrium supply, whose suspension begins producing operational consequences within the existing inventory depletion timeline. The cumulative picture across 17 elements is consistent and alarming. American military capability is not primarily limited by the quantity of weapons it possesses. It is limited by the rate at which it can manufacture and replace weapons, and the rate at which it can manufacture weapons is limited by the availability of the 17 elements whose supply China suspended this morning. I want to walk through the military production impact with the timeline specificity that the strategic situation demands, because the mainstream coverage has treated the rare earth suspension as a long-term concern rather than an immediate operational crisis. The timeline from supply suspension to operational capability degradation is not long-term. It is measured in weeks to months, depending on the specific production line and the specific element inventory that exists in each manufacturer's supply chain. Let me walk through the critical production lines and their specific timelines. F-35 production, Lockheed Martin, Fort Worth. Current neodymium dysprosium inventory at Lockheed Martin's primary magnet supplier, approximately 90 days of production supply at current build rates. After 90 days, F-35 production halts at Fort Worth. After production halt, the 12 allied nations whose F-35 orders are in the production queue, Japan, South Korea, Australia, the United Kingdom, Italy, the Netherlands, Norway, Denmark, Belgium, Poland, Singapore, and Israel, do not receive their aircraft. The combined F-35 backlog represents approximately 350 aircraft whose delivery cannot occur without rare earth supply restoration. 350 aircraft for 12 nations whose air forces are integrated into the American alliance system at the operational level. Precision munition production, Raytheon, Boeing, Lockheed Martin. The guidance system components for JDAM kits, small diameter bombs, JSOW glide weapons, Hellfire missiles, and AMRAAM air-to-air missiles all require terbium and europium in their optical and electronic components. Current production inventory assessments across the major precision munition manufacturers suggest guidance component supply for approximately 60 to 120 days at current production rates, depending on the specific munition type. After inventory depletion, precision munition production rates drop to the levels supportable by non-Chinese rare earth supply, 5% to 8% of current production rates based on available non-Chinese processing capacity. 5 to 8% of current precision munition production, in the context of a conflict whose consumption rates this series has documented: 50% Patriot interceptor depletion, 30% Tomahawk depletion. The reduction of replacement production to 5% to 8% of current rates is not a supply chain challenge. It is the permanent end of American precision munition inventory replenishment at operationally meaningful rates. Semiconductor production, Intel, AMD, NVIDIA, Qualcomm. The semiconductor fabrication processes that produce the advanced chips powering American military electronics, American artificial intelligence systems, and American communications infrastructure require cerium polishing compounds in the chemical-mechanical planarization process that produces the flat surfaces on which circuits are printed. Current cerium polishing compound inventory across American semiconductor fabricators, approximately 30 to 60 days of production supply. After inventory depletion, semiconductor production rates for advanced chips drop to levels supportable by non-Chinese cerium processing, approximately 12% to 15% of current production rates, 12 to 15% of current advanced semiconductor production. The military electronic systems, the communications infrastructure, and the artificial intelligence capabilities that American military operations depend on are built on semiconductors. Semiconductors whose production has just been reduced to 12% to 15% of current rates. The operational consequence of military electronics production at 12% to 15% of current rates reaches deployed systems within the replacement cycle for their degraded components, approximately 6 to 12 months for the most critical systems. Naval Electronics Combat System Integration. The Aegis combat systems on American destroyers and cruisers, the APG radar systems on American fighters, and the electronic warfare systems that have been documented throughout this series all contain rare earth-dependent components whose replacement requires the rare earth supply that has been suspended. The combat system maintenance cycle for American naval vessels requires continuous component replacement whose supply has just been constrained to 5% to 15% of normal rates depending on the specific component. A naval fleet whose combat system components cannot be replaced at their degradation rate is a naval fleet whose combat effectiveness degrades systematically from the moment of supply suspension. The degradation is not immediate. It is cumulative, and it is permanent unless the supply chain is restored or replaced. I want to address the alternative supply timeline with the honest assessment that the strategic situation demands. Because the question that every government official, every defense analyst, and every mainstream commentator will be asked tonight is the same question: why did we not build the alternative supply chain before this happened? The answer requires honest assessment of both the technical timeline and the political economy that produced 30 years of insufficient response. The technical timeline for building a complete alternative rare earth supply chain, from mine development through processing infrastructure through manufacturing adaptation, is 10 to 15 years under optimal conditions. Let me explain why that timeline is determined by physics rather than by political will or financial investment. Step 1, Mine development, 3 to 7 years. The rare earth deposits that exist outside China in the United States, Australia, Canada, Brazil, and several African nations require development timelines of 3 to 7 years from exploration confirmation to first production. The timeline is not primarily determined by the construction of the mine itself. It is determined by the environmental permitting process, the infrastructure development required to access the deposit, the processing facility construction adjacent to the mine, and the workforce training required to operate rare earth separation chemistry safely. The Mountain Pass mine in California, the largest rare earth deposit in the United States, was closed in 2002 due to processing waste environmental violations and required 15 years from closure to resumption of production at meaningful scale. 15 years for a mine that already existed. Step 2, processing infrastructure, 5 to 10 years. Mining rare earth ore produces a concentrated material whose rare earth content is typically between 1% and 10% by mass. Separating the individual rare earth elements from this concentrate, a process known as solvent extraction, requires chemical processing infrastructure of extraordinary complexity. The chemistry involved, including solvent formulations, temperature control, pH management, and separation column configurations, represents industrial knowledge accumulated over more than 30 years of Chinese production experience. Building rare earth processing infrastructure is not simply a matter of financial investment. It is a matter of technical expertise and industrial knowledge. Most of the engineers and chemists with experience in large-scale rare earth processing are located in China. Developing equivalent expertise elsewhere requires years of training and experience that cannot be accelerated easily through funding alone. Even after mining and processing infrastructure is established, manufacturing systems must still adapt to alternative supply sources whose chemical specifications may differ from Chinese processed materials. Fighter aircraft magnet manufacturers, precision-guided munition producers, and semiconductor fabricators all operate with processes calibrated to the exact specifications of Chinese rare earth compounds. Adapting production systems requires testing, qualification, engineering adjustments, and manufacturing line modifications, which may take an additional 2 to 5 years. When combined, the total timeline for establishing a complete alternative supply chain, including mine development, processing infrastructure, and manufacturing adaptation, is estimated at 10 to 15 years under ideal conditions. The failure to build alternative supply chains over the past 3 decades was not simply a political failure. It was largely the result of economic calculations that favored lower-cost Chinese production. Building supply chain redundancy outside China required significantly higher costs, while companies focused on maintaining competitiveness and reducing expenses. As a result, manufacturing and processing capability became increasingly concentrated in China. For years, governments were warned about the strategic risks associated with rare earth dependence, but many assumed market forces would eventually correct the imbalance if necessary. Instead, the dependency deepened, and reversing it now requires years of industrial reconstruction. China's ability to restrict rare earth exports has existed for decades. The critical question is not whether China could do this, but why it chose to act now. One major factor is the depletion of military inventories. Ongoing global conflicts and defense commitments have consumed large quantities of advanced munitions, missile interceptors, and military hardware. The suspension of rare earth supply does not create shortages from zero. It interrupts the replenishment of inventories that are already under strain. When inventories are already depleted, even short-term supply disruptions can have immediate operational consequences. Another factor is diplomatic leverage. Strategic tensions surrounding reconstruction agreements, ceasefire arrangements, and regional military calculations have increased the importance of maintaining military readiness. Confidence in sustaining future military operations depends heavily on the ability to replenish advanced weapon systems, and those systems depend on rare earth supply chains. Taiwan also remains a central strategic consideration. Any prolonged disruption to American and allied manufacturing capability affects long-term military planning in the Indo-Pacific region. A military capable of replacing equipment during an extended conflict operates very differently from one forced to ration existing stockpiles because production has slowed dramatically. China's dominance in rare earth processing was not accidental. It was the result of decades of industrial policy designed to build control over materials essential to modern technology and defense manufacturing. Over time, investment, infrastructure development, and technical specialization allowed China to dominate the industry while many other nations reduced their domestic processing capacity. The challenge facing the United States and its allies is that there is no immediate solution. Emergency stockpile releases, allied coordination, and prioritized military production can provide only temporary relief. Long term recovery still depends on building alternative mining, processing, and manufacturing systems that require years to establish. Governments are expected to respond with emergency funding, industrial incentives, accelerated permits, and strategic investments, but such measures cannot quickly solve the immediate supply problem. The operational timelines of military production are much shorter than the timelines required to rebuild industrial capability. The economic impact also extends far beyond the United States. Japan, South Korea, Germany, France, the United Kingdom, India, and other manufacturing economies all depend heavily on rare earth materials for electronics, vehicles, industrial equipment, and defense systems. Supply disruptions affect domestic manufacturing, employment, and economic stability across allied nations. The broader issue highlighted by this situation is the relationship between economic interdependence and strategic independence. Modern military power does not rely solely on weapon systems. It depends on industrial capacity, raw materials, advanced manufacturing, and secure supply chains. For decades, rare earth dominance developed quietly through supply chains, industrial investment, and market economics, rather than through visible military expansion. What now appears as strategic leverage was built gradually over 30 years through industrial concentration and global dependency. Today, those dependencies have become impossible to ignore.